Welcome everybody to the celebration of the 50th anniversary of Plate Tectonics at Scripps Institution of Oceanography. My name is Brian Aller. I'm a grad student here at Scripps, and I had the privilege of serving on the committee that put all this together. The organizing committee started working on this project we started working on this project last summer with John Slater. And during a meeting with Donna Blackman, she suggested that the students actually lead the entire symposium, that we organize the whole thing from the ground up, as opposed to have some faculty advisors doing the heavy lifting for us. And that was a great idea because that's what really makes the symposium unique compared to some of the others that have happened here recently. This symposium is actually organized by graduate students and a postdoc. So before we get started, I'd like to thank Donna Blackman and John Slater for all their help and getting us set up and getting us the resources that we need to make this possible. Can I get a round of applause for those folks, please? Next, I'd like to thank the organizing committee, Jesse Saunders, Emily Way, Dana Prusak, Ishita Powell, Travis Clough, Kate Durkin, and Carrie McIntosh. You guys did an incredible job putting all this together, and you did it in a very short amount of time. I'm proud to have worked with you guys on this. Thank you. I would also like to thank Kathy Constable, Guy Masters in the Director's Office, IGPP, the Geosciences Division, our great administrative staff that kept everything online and under budget and on time, and all of our generous donors. We really appreciate this opportunity to put on this symposium for everybody. We all came here this morning to celebrate some outstanding works of science, but we're also here to connect with our history, a tradition of this world-class, one-of-a-kind research institution out here on the beach. Many of the foundational contributions of the theory of plate tectonics were made by graduate students, particularly the ones that came from Scripps. At the time, these people weren't very different than the folks that organized this committee, and weren't very different than a lot of my colleagues that are sitting out in the audience right now. Over the next 2 days, these remarkable scientists have agreed to talk to us, or they've agreed to talk with us, and share their stories and their experiences in putting together this game-changing story. Many of them traveled a great distance to be with us today, and they did so with absolutely no hesitation when asked. So let's get a big round of applause for all of our guests that came here to be with us today. So on behalf of the entire organizing committee, I want to thank all of you for coming out here today. I know you probably have other things to do, but you came here instead, and that means a lot to us. So thank you all for coming out, and I hope you have a fun and exciting symposium. Up next is our first speaker. She's going to be giving our welcoming address. She's made outstanding contributions throughout her career in the fields of marine geology and geophysics, and she was instrumental in helping us get all this put together. Ladies and gentlemen, please welcome Dr. Donna Blackman.
Well, good morning, everyone. I'll stand here and not shout. It's a pleasure, actually, to see this group and this mixed group of people. You know, we're quite a suite of scientists. A lot of us marine, a couple that are a little bit less marine, but still fundamental to kind of putting together the mathematical background for what underpins plate tectonics. But anyway, it's as Brian said, I'm just really pleased that you all have taken the time and agreed to come out here and help us celebrate the ways that Scripps contributed to plate tectonics and getting the word out. I mean, I think there's both the science itself, which of course was outstanding and insightful, and then the choices of how to communicate that, because of course that was a challenge. These were ideas that not everybody was ready to embrace, and I think that's one of the messages for the student group here is, you know, how do you go about that when you're starting to recognize something new and not everybody's ready for that? How do you persist? How do you break in? And, you know, how do you choose your audiences and your publications in a way that can be effective and ultimately turn people around? So I don't want to speak a long time. The whole point here is to hear from you. But I do want to welcome you back to Scripps. Many of you haven't been here in a little while. It's great to have you here again. We'll proceed through the morning. You've all seen the schedule, but just to quickly remind you, we'll have a break, kind of mid-morning, and then we'll have lunch. And then the posters that we get to actually see some of the work from the students themselves. What are they working on today? And give them some feedback on how their work is coming across. Those of you that haven't found the restroom, just logistics, there are restrooms just outside here on this floor. You kind of go around the corner. They're a little bit tough, so if you haven't seen them, this is a new building. Many of you haven't seen this building here before, and it's a wonderful facility. So anyway, let's go ahead and get right started. And Chris Harrison is going to kick us off here with scripts, seafloor spreading, and the transition to plate tectonics.
Thank you, Donna and Brian, and thanks, Donna, for some of the logistics there. I do have a few more orders of business before I introduce Chris Harrison. The format of this symposium is that we have 2 to 3 talks followed by a discussion. So we would like to ask you to hold your questions until the discussion section. For the speakers, Jessie is going to be our official timer, and she is going to stand when you have 2 minutes left and raise your hand when you need to be off the podium. Another item is that all graduate students need to sign in at the registration table so that we can get money from GSA. And though it is also not advertised on all versions of the schedule, we will have a happy hour tomorrow, Thursday afternoon from 3:30 to 5 p.m. in Surfside, which is right there. So get excited for that. And finally, should you need any assistance throughout the day, you can find one of us wearing these name badges with organizer on it, and we would be happy to help you. Now I would like to introduce our first speaker, Chris Harrison. We owe advances in the field of plate tectonics to the marine magnetists, whose work was pivotal to describing seafloor spreading. Chris Harrison utilizes the powerful tools of marine magnetics to solve problems in plate tectonics. Though his graduate degree is from Cambridge University, he spent most of his graduate studies at Scripps focusing on magnetization of deep-sea sediments. His dissertation work showed that these sediments record reversals of Earth's magnetic field. By comparing reversals recorded in both sediment and marine basement, scientists now have the ability to date sediment based on its magnetization. After completing his PhD at Cambridge, Chris spent 3 years as a postdoc at Scripps and spent his career at the University of Miami, where he has been now for 50 years. His paleomagnetic studies have been used to constrain tectonics and volcanism in Mexico, constrain plate motions, study the magnetization of seamounts, and produce a polar wandering curve for North America. With other collaborators, he has also produced maps of continental locations for the past 180 million years. Throughout his career, he has held advisor positions in AGU, the drilling program, and AAAS. Please join me in welcoming Chris Harrison.
Save some time because you don't need to say anything about Chris. I just wanted to point out that this is a saying inspired by Rutherford. It's true that it's impossible to talk about all the people who've been involved in plate tectonics, so I'm only going to talk about a few. And the reason I'm here is that I read a paper by Rampino in EOS, and it's the start of plate tectonics. And his data were from a small private college in Princeton with only about 25 people there, 19 Americans, 5 from UK, and 1 Canadian, so it didn't really cover the gamut of where people are. So I started to write a comment about this to fill in some of the gaps, and I sent my comment off to EOS, and they said, well, who do you want to review it? So I said, John Slater and Mike Fuller and another. And I got 2 very good reviews, so they're publishing it sometime. Anyhow, so it's been a battle. This is a quote from Jeffries' The Earth. The arguments against convection in the Earth in its present state, continental drift, and now plate tectonics are greatly expanded. So these are arguments against all these three things. So he didn't believe in that. Also in that volume of the Earth, he talks about working with magnets. And he said about 1909, he said that if you drop the magnets, they lost their magnetization. And he couldn't figure out how rocks, after they've been hammered off the cliff face, could retain their magnetization. So it's been about. But the first person to do a good job at putting things together was Alfred Wegener. And he thought that in order to understand the Earth, you had to put different parts of Earth science together. In particular, geophysics and paleontology. And he used paleontology to fit the continents together, and geophysics to say that you go down far enough, it gets hot, and therefore everything gets plastic, so that it could be some sort of convection going on. And he thought that what was happening in paleontology and geophysics was what Rutherford described as stamp collecting. So he wanted to put these things together and get something useful out of it, and he did. His upper Carboniferous here, you can see that the Gondwana continents, South America, Africa, India, Antarctica, Australia, and New Guinea are all together close to the South Pole. So this is an amazing accomplishment for somebody who was not a geologist, but was a meteorologist who lost his life in Greenland. Another important person was Alexander du Toit, who was a South African, and he had studied South African geology for a long time, and he was given some money from the Carnegie Institute to do fieldwork in South America. And when he compared the geology of the two continents, South Africa and South America, he figured that there was lots of connections, so he put them together as one continent. You can't see it very well, we'll show you a picture of it later on. And he was recognized by geologists like Moses medal, a medal that was given to Harriet Jeffreys and Arthur Holmes a few years later. And of course, one believed in continental drift and one didn't. So this is his hand-drawn map of South America, Africa, India, Madagascar, Antarctica, Australia. So a very reasonable thing, but it's not quite right to get out of that. One of the things that he did in his book is to make a list of people who were not going to believe in him. And what I like is the quote, almost certainly the majority of geophysicists will not believe in him. But he did have some active protagonists, Taylor, Argand, and Holmes, and other people. Arthur Holmes was also very important because of his dating. I just put this here to show it here. He had some effort to do this dating because he was one of the first people to actually date rocks using radioactive techniques. He wrote a book which is very well known in Britain, The Principles of Physical Geology, and certainly when I went to Cambridge, that was the book we all read. And in the 1947-45 edition, it had 33 pages on continental drift, and in the next, the third edition, it had 62 pages out of 717, almost 10% on continental drift. So he was a great believer, and having read that book, you were inclined to believe that this thing existed. I just wanted to say that his dating of the Earth was not being approved by Lord Kelvin, who of course long gone. This is a young Arthur Holmes. person that influenced my career was PMS Blackett. He was a Nobel Prize winner in physics from Cambridge. He was president of the Royal Society. He was made a life peer, Lord Blackett. And one of the things he did was to build a very sensitive magnetometer. And what he wanted to do was to test the hypothesis that rotating matter created a magnetic field, and people had said how big this should be. And he calculated, and this is because they knew that stars have magnetic fields, but they didn't know anything about dynamos. But so he built this magnetometer, and there was a negative experiment. There was a wonderful write-up in the Royal Society about this, showing how to get a very sensitive magnetometer. He had two choices. One was an astatic magnetometer, and the other was a fluxgate magnetometer. The fluxgate required electronics, and despite the fact that he had been in the war in operational research, he didn't like electronics, so he chose to build an astatic magnetometer, which is very easy to build, and other people built them and started the process of looking at the paleomagnetism of rocks. But he had gathered data, he and his colleagues gathered data from North America, Europe, India, and Australia. And these points are Denver, Paris, Nagpur, and Alice Springs. And of course, with paleomagnetism, you can tell the latitude because if you have an axial centric dipole, the tangent of the inclination is equal to twice the tangent of the latitude. So if you can measure the inclination, you can tell the latitude. So that's what these points are. They're showing the latitude of these various, starting off with Paris and Nagpur, and which is incredible because as it goes through time, you can see that the Nagpur has come from here to here in 150 million years. That's an average of about 55 millimeters a year. And the declination, which is the direction of the horizontal perpendicularity, you see the angle that these things make with the meridian. And so from here to here, North America is rotating counterclockwise to get from here to point up here. And that was the thing that impressed me, and that's why I decided to do paleomagnetism. And I have to say that I went to Cambridge wanting to do geology, but half of the first year was invertebrate paleontology, and you had to know 100 fossils. Half of the second year was paleontology, micropaleontology, invertebrate paleontology. You had to know 400 fossils. And I figured in the third year you'd have to know 900 fossils. So I started after 1 year and did physics. But Blackett came and gave a talk in the Cavendish, which I went to, and I said that, and I remember this figure from that talk, and that's what I decided to do. And I found there was a geophysics department at Cambridge, which was completely separate from anything else going on in the university. It was out on Madingley Road, and I was accepted as a student there. One of the things that was not talked about at all in the Rampooner article was the fact that there were two scientists, one from France and one from Japan, that were very important in determining how rocks got their magnetization. And Tellier is still known because there is a Tellier method of measuring the intensity of rocks, and there's a modification of that is still being used. I couldn't find a picture of him, but this is Nagata. His main claim to fame was with Seio Ueda Nakimoto. He founded a rock which had self-reversal qualities. You heated it up in a normal field, it became reversely magnetized when you cooled it down a bit. And that was an interesting thing, but it was understand how rocks become magnetized. Harry S. was at the meeting in Princeton, but he didn't seem to have given a talk. And so he did publish a paper, a long paper, in this volume here. I put this up because during the war, Second World War, he was a reserve naval officer who ran a supply vessel around the Pacific, and he kept his echo sounder on all the time, which was, of course, strictly against the rules because of the fear of a submarine finding it. But he found things like EOs, which he named, because they're flat-top sea mounts. And EO was a chair of the geology department at Princeton for a while, as was Harry S. But in his paper that I've just mentioned, he had a lot of things to say. This is in 1962. The matter is convecting 1 centimeter a year. That's probably pretty slow, but it's some of the right order of magnitude. Convecting currents have rising levels beneath the ridges, and convecting currents count for the topographic rise of mid-ocean ridges and for the high heat flow there. Both of these things seem to be correct. The ocean is swept clean every 300 to 400 million years. It's pretty long. The present day maximum age of the ocean crust is 180 million years, and the average age is 60 million years. So this is a bit long, but it's still in the right order of magnitude. And because of the fact that it's fairly short time, the sediments, of course, are very thin, and in the ocean, there are no oceanic rocks older than the Jurassic, but he said Cretaceous was very, very close. The currents carried on convecting matter, they didn't plow through ocean crust, which was thought to be one of the ways in which they got around, but he was saying the ocean crust moves with them. The ocean column is isostatic equilibrium with a continental column. That is absolutely correct. And the oceans are impermanent things and the continents are permanent. So these 9 things seem to be things that we believe in today, and he prophesied that that's what was happening a long time ago. So we get to come to the Scripps collection here, and there were people we might know: Dick von Hertzen, Roger Revelle, Gustav Arrhenius, and Russell Raitt, Ron Mason of the Mason-Rack Lineations, Art Maxwell, Walter Monk, and Helen Raitt. You notice that they're all men except for Helen, and Helen and Russ were great friends with the Revelles. Roger Revelle wanted to have Rachel Carson, the writer of The Silent Spring, as a person on his cruise, and he had to show that they could deal with women. So he invited Helen Raitt to go, and she went and wrote a wonderful book about it. I have to confess that these are my parents-in-law. So one of the things that happened here was people discovering the Mason-Rack lineations. Ron Mason was a faculty member at Imperial College in London, and Art Graff was a technician. And of course they put together these stripes, which are very important because they show what the magnetic field is doing to the rocks as they come out of the crust, out of the mid-ocean ridge. But they didn't know this at the time, and this was all made clear later on. One of the people who used this actual document to write a paper was Larry Morley, and he is not very good. This is the same thing as we saw that last slide. But he wrote a paper in which he said that these things were caused by reversals of the Earth's field and by seafloor spreading, and he sent it off to Nature. It was rejected, and it was sent off to JGR, and the editor who rejected it said, It was the sort of thing that one would talk about at a cocktail party, but one would not try to pass such thoughts under serious scientific aegis. What a mistake that was. I haven't found out who the editor was yet, but I was trying to. Okay, Vic Vaquier was an important person. He invented the fluxgate magnetometer. And it was the fluxgate magnetometer which was used in the Pioneer survey, which was the thing that I just showed you. And it was a very peculiar instrument because fluxgates, of course, they measure the component of the vector. And so they had three fluxgates, or right angles to each other. And the two of them were moving so that they recorded zero field. So the third one was recording the total field. It was very complicated, and the proton precession magnetometer was much easier because you had to have a bottle with a coil around it and the way of counting things, so it was pretty easy. Anyhow, and he used the proton precession magnetometer to do these profiles, and what you see here, this is the Mendocino fracture zone, this dashed line. This is the Pioneer fracture zone, and this is the Murray fracture zones. And to get the anomalies north of the Mendocino to agree with the ones between the Mendocino and the Pioneer, they had to be moved from this amount, which is 1,400 kilometers, and then from the Pioneer to the north of the Murray, you had to move another 260 kilometers to the right, and then to get these things to fit on to the ones above the Murray, you had to move them to the left, 680 kilometers here, and only 200 kilometers here. And of course, the reason for this was not known. It was explained by Tuzo Wilson's transform fault hypothesis. Yes. Okay, so some of the work that I did was in ocean sediments, and what you see here, and these were cores, gravity cores taken very close to the equator, so the magnetization was basically pretty horizontal, the horizontal being around the edge, and this being vertical up. And you see there are two groups, one group up here and one group here. We don't know the actual orientation because we didn't have an orientation device, but it's fairly obvious that these represent one polarity, and these represent another polarity. And that's the same is true of this core too. There are two groups of poles. And if I go to the next slide, you will see that if you arrange the things into normal and reversed, and these are where the data were collected with the little cores out of the big core, you can see you have normal at the top, then you have reversed next, and then you have normal, a little reversed here, normal here, and then reversed at the bottom. Of course, the timetable of reversals was very different in those days, but this did show that the sediments retained their magnetization well enough to date them. And next we have Russell Raitt, and he gathered all the data together for doing some of the seismic refraction in the ocean, which basically measures the velocity of the layers and their thickness. And so here we have layer 2 with a velocity of 5 kilometers per second and an average thickness of 1.7, and then the mantle at 6.69 kilometers per second. Very different from the continents, which are much lower than that, the mantle, called their continental crust, and a thickness of close to 5 kilometers, again, much less than in the continents. this is a typical mantle velocity. So the total ocean crustal thickness, the thickness of these two layers is about 6.6 kilometers. And of course the continental crust is like 42 kilometers. And so these are two more modern estimates. So now we come to Teddy Bullard, Sir Edward Bullard. He was head of the Department of Geodesy and Geophysics for a while at Cambridge. And he had invented the Bullard probe, which allowed people to measure heat flow. The first measurements in the Atlantic were made by Bullard, Maxwell, and Rebel in 1956. Maxwell and Rebel being in that picture that I showed. And they showed an average heat flow of 1 microcalorie per square centimeter per second, which in modern units is 1.8 milliwatts per square meter. And this is very peculiar because it's about the same as what continental heat flow measurements were. It was thought that continental heat flow came from a thick oceanic continental crust, which had lots of radioactive elements in it, which caused the heat to be there. Whereas the ocean crust didn't have many of these radioactive elements. And certainly the mantle is very few, so comparing the oceanic crust to the continental crust and getting the same result was pretty odd. Now we can explain that. So they said something, the rough equality of oceanic and continental heat flow can scarcely be a coincidence. Of course it was a coincidence. Now I'm going to tell us the story of how Teddy became a geophysicist. And this was told us, we had, John Slater and I organized a little conference for Teddy when he was basically dying, where he was living in La Jolla. And in the evening we had the people talking about what Teddy was like. And one of the people who gave a very interesting story was Keith Runcorn. And he pointed out that Sir Gerald Ernest Cunningham, who was a reader in geodesy, wanted to have a student to work for him, his physics student, to help him teach the people that he had learning geodesy at his department. So he arranged to sit next to Rutherford at dinner one evening, and after they had talked about the niceties of life, Sir Gerald said, well, can you recommend somebody to help me teach geodesists? And Rutherford said, talk to Bullard. So Sir Gerald did not know what to mean about this, but he saw Rutherford a few days later in the street, and he said, are you sure about Bullard? Rutherford said, yes, he's a damn sight better than you. So he hired him. Now, I haven't talked about the famous map that was put together of the continents around the Atlantic, because everybody knows it. And what I want to do is to talk about this paper, which compares Bullard's fit with all these other fits, and I'm sorry, John, that you're here. So what if this is, these are polar wandering paths for North America and for Europe for the periods of time that it was thought that they were together. So what Rob van der Loo did is to rotate the European ones by all the rotations given by these various papers, and then compare the latitudinal difference and the longitudinal difference between the results. And you can see that you can see that the white things have now been rotated, and they agree very closely with the black ones. And this is using the Bullard et al. Fit. And you notice that all the others, the longitudinal difference is quite large, especially for this one here. and this means that they were much less tight. And so this is a good confirmation that the bullard fit around the Atlantic was actually pretty good. So the last thing I want to talk about is heat flow, and this is the result of a cruise in which Dick von Hudson and Sarah Viega were the chief people, but I was a slave. I had to do a lot of the heavy lifting. And this is a profile across the East Pacific Rise, and you can see that there are some very large heat flow things, and of course we now know why this is the case, and we now know also why there are very low values here, because if you happen to have a sediment pond which is very close to rocky outcrops, the heat is escaping through the rocky outcrops and not through the sediment, so you measure low values. And other people producing data were Bullard, Rubel, and Maxwell, as I've already said. Now, this is the end of the beginning, as was a quote from Winston Churchill, and we'll now hear other things about plate tectonics and